Namaste dear participants, welcome again to the Swayam course on image processing using Python. I am Dr. Atul and continuing the tutorial from the previous session. Therefore, it is recommended to you to watch my previous session videos before continuing to this tutorial. Before going further, let us discuss some outline of this session. In this session, I will discuss about image edge detection techniques, which include edge detection filters. I will discuss first order gradient based edge detection, also second order gradient based edge detection as well. First order gradient based filters, we will explore three operators. First one is Sobel operator, second one is Prewitt operator, and third one is Robert operator. Operators are actually filters. Therefore, you can also say Sobel filter, Prewitt filter and Robert filter. In the second order gradient operators, we will explore Laplacian operator, Laplacian of Gaussian filter and Canny filter. At last of this session, I will conclude, I will tell you what are the outcomes, what we have learnt through this session. Edges are significant local changes of intensity in a digital image. An edge can be defined as a set of connected pixels that forms boundary between two regions. There are three types of edges. First one is horizontal edge, second one is vertical edge, and there are diagonal edges too. But most of the filters works for horizontal edges and vertical edges only. Edge detection is a method of segmenting an image into regions of discontinuity. It is widely used technique in digital image processing for the purpose of feature extraction, for the purpose of pattern recognition, for the purpose of morphology. So, morphology, pattern recognition and edge detection or feature extraction, this edge detection is very important. Edge detection allows users to observe the feature of an image. Edges indicate a significant change in the gray levels of the image. This texture indicating the end of one region in the image and the beginning of other region. It reduces the amount of data in an image and preserves the structural properties of the image. The filters used for edge detection are of mainly two types. First type of filter is gradient based filter, which computes first order derivations in the digital image. Like the examples for these type of filter is Sobel filter, Prewitt filter, Robert filter. Second order gradient based filters which compute second order derivative or second order gradient in the image. So, the example of these filters are Laplacian filter, Laplacian of Gaussian filter and Canny algorithm or Canny filtering algorithm. Let us go to first one, that is gradient based filter. So, edges can be easily detected by observing the gradient change in the pixel values of the image. You remember the basic mathematics that if we have a curve and we want to find out maxima and minima, maxima or minima, that is maxima or minima is change or edges. So, what is the way? The way is to differentiate the function. Differentiation means edge, the gradient, that the same concept is applied in the images. So, pixels in images are located at discrete points. Therefore, instead of differentiation, we use difference operator. We take differences of the pixels because it is in the continuous domain. Filters actually try to evaluate the gradient. The filters like Sobel filter or whatever filter or for the edge detection, they actually evaluate the gradient or approximate value of the gradient for edge detection. The Sobel filter computes the gradient approximation of the image intensity function for image edge detection. At the pixel of an image, the Sobel operator produces either normal to a vector or corresponding gradient vector. The Sobel filter is actually the set of filters or set of coefficients that calculates the gradient. So, these coefficients are very good. So, these coefficients actually when you apply this filter or when you convolve this filter to the image, then gradient will come as a output. That is the beauty. First one is for the x direction and second one is for the y direction. So -1, -2, -1 in first column and third column 1 to 1, and these are the conjugate of this is for the y direction. The filter, Sobel filter, is very simple and efficient and very easy to design, but the problem is that horizontal filter is available, vertical filter is available, but for diagonal edges there is nothing, and it is highly sensitive to noise also, and filter coefficients are very fixed. So this cannot be changed, that is also a problem. So in every language we are dependent on libraries. Only some languages like MATLAB, there we don't have to include the library, but in most of the languages we have to include the library. So if you want to work on Python for edge detection, first you need to specify the libraries, and then if you are using Google Colab as IDE, then you need to mount Google Drive to interact with the images from the Google Drive. And if you want to know how to do all these things, how to import libraries, how to mount the Google Drive, you can watch my previous videos. Also, in this session I will use show image function to show the image and plot comparison function to plot two images at a time. These two functions also I have coded in the last session for displaying the image. Show image is to display one image and plot comparison is to display two images side by side. And if you don't remember how to do these functions, then go back to the previous video and watch how to do that. In order to apply the 2D filters, we need 2D convolution also. Here I am importing 2D convolution from SciPy library and reading the image, and then I am creating matrix for Sobel filter using the NumPy, and then I am applying this to the image using convol 2D function. You can see the result. The image coming right side are the edges of the image. To apply this Sobel operator, we have to use convolution 2D, and here I am applying the operator to the image. So image, and then kx is the horizontal operator. So from the convolution, after the convolution, gx is coming horizontal output. We can see the horizontal output and the image input together by using the horizontal edge detection by using the plot comparison command that we have already defined. And for the y direction, I have to use the ky. The ky is actually the conjugate of the x. So and then if you want to see both of these, means original image and y direction edges, then we have to use plot comparison command. Then now if I want to see horizontal edges and vertical edges both together, then what I have to do? I have to take absolute value of the both. So here I am taking geometric mean, means root over x square plus y square as a rule. So then the overall will come. Then you can plot the overall with respect to the image. Now you can see the result that above one is for the vertical edges and the last one is the edges. So we can see that horizontal edge detector is incomplete, vertical edge detector is also incomplete, but the overall edge detector is fine and perfect. Now let us go to the another filter of using the gradient. It is very similar to the Sobel filter, although the results are very similar to the Sobel filter, but still innovation of this scientist Prewitt is that he have not used the same coefficient, he have given new filter coefficient. It also detects vertical and horizontal edges of an image. It is one of the best way to detect the orientation and magnitude of the image. The set of filter coefficient is also called kernel or mask. So many times if I say mask, if I say kernel, that is the filter matrix actually, that is the filter coefficient set actually. So therefore do not get confused in this filter, mask and kernel, all three are same. Now what actually Prewitt had given, the horizontal filter that Prewitt had given as the number, the first column is -1, -1, -1, second column is 0, 0, 0, third column is 1, 1, 1. The conjugate of this for the y direction, the first column is -1, 0 and 1, second column -1, 0 and 1, and third column -1, 0 and 1. The process to apply these kernels starts now. You have to create the matrices for these two first. So first matrix is stored in the A1, NP dot matrix 1, 1, 1, and second matrix is stored in A2, NP dot matrix -1, 0 and 1, and then Kx is created by A1 transpose into A2, and then I am printing Kx just to see whether the filter is created is same or not. Then Ky A2 transpose into A1, and to apply this operator we have to convolve the image with Kx first. It is using the same and symmetric. What that means? Same means the output will be of same size as image size. Therefore convolution 2D here will the result in Gx, and Gx will be of same size, the same number of rows and same number of column as that was in the image. Now if I want to see the image, then I have to use the plot comparison command that is available to us. So plot comparison command, in this I have used original img and Gx, and horizontal edge detection will be shown as a title of right side image. You can see the results now. Here you see left side image is the original image, and when I had applied the horizontal edge detection, you can see that right side image coming, that edges of this image are being detected. So if I want to see the vertical edges, so I have to do the same process. Process is same. You just have to apply two-dimensional convolution to it. Take the image, take the y-directional filter, and same is written to produce the same output as the size of the image. So Gy will give you the same output as the size of the image, and to see both original and the filtered image you can use plot comparison img.gy. So then it will give you the vertical edge detection, and you know that if I want to have the complete edge detection with the help of these horizontal edge detection and vertical edge detection, what I have to do? I have to take the geometric mean of this, that is root over x square plus y square, and g equal to root over x square plus y square. That will show the resulting image. So to see the resulting image we have to use plot comparison command, and then the right side title is overall edge detection. So you can see the result, and you can see the image that actually the overall edge detection works well and provides a better result. There is another way to do this. Instead of using root over x square plus y square, you can also take the absolute value of x plus absolute value of y. This will provide the results also similar to the previous one. So there can be many n number of methods of taking the values from x and y, combining the values of x and y. The next is Robert filter. Robert filter is even smaller filter as compared to the Sobel filter and Prewitt filter. So here we use 2x2 kernel instead of 3x3. That is also very nice. It enhances the computation time of the filter. So gradient based Robert filter it takes sum of the square of differences between diagonally adjacent pixels through the discrete differentiation. It uses the kernels or mask of 2 by 2 size. The mask values are for first column -1 and 0, for second column 0 and -1. For y direction, you can take conjugate of the x direction mask. So this is very useful, and this was suggested by Roberts. Therefore, this filter is called Robert filter. Now in Python, first we have to create a matrix for x direction filter, then we have to create a matrix for y direction filter. Procedure is same as we have used procedure in the x direction is of Robert, as we have used procedure in x direction of the previous filter Sobel. Similar process can be used here also, and we have to use convolution, and after convolution we have to use plot comparison, and this will result in the this will give you the comparison of the images in xy direction. Then at last, when you are calculating the absolute or overall edge detection of the image, then you have to take the root over x square plus y square, means the result of x square plus the result of y square and square root of the complete. Then instead of using the square root of x square plus y square, you can use absolute value of x plus absolute value of y. There is no problem, and the result will be approximately same in the both of the type of systems. You can see the results, all results are compared here. Now we are going to little advanced kind of edge detection method, that is the second order derivatives, and it's called Laplacian filter. Laplacian of an image, it highlights the areas where there is rapid change of intensity, and it can thus be used for edge detection. You remember when we do maxima and minima, again I am coming back to the basic mathematics, and maxima and minima, if we are not able to identify the maxima or minima with the help of the simple differentiation, then we do the second order differentiation. That is what is here. Here we are doing the second order differentiation. If we have IXY image, then IXY represent the intensity of an image, then the Laplacian of this image is given by Laplacian of xy is equal to del square upon del x square I plus del of del y square I. The peak or bump in the first order gradient differentiation represent the edge. Then tell me how to get the edge using second order derivative. Just think, when we were doing maxima and minima in the calculus, then what is the way to get the maximum minima? By using the second order derivative. Pause this video for 30 seconds, think in mind, and then write in the notebook and say the second order derivative of a function, the value is 0 at maxima and minima. Usually for calculating the second order derivative, the values are 0, 1 and 0, 1, minus 4 and 1, and 0, 1 and 0, and the conjugate or for calculating other, it can then the second order derivative minus 1, minus 1, minus 1 for the first column, then for the second column minus 1, 8 and minus 1, and for the third column minus 1, minus 1, minus 1. Considering the constraint of time, I am using a built-in function for this purpose without doing the detailed implementation of it. Using OpenCV library, we will implement this, we will do coding. So the cv.Laplacian, this command is available in the OpenCV library. So you can apply this command to your IMG file, and the resultant will be a new image. Then you can define the figure size, and plot comparison command that we had defined in the starting, this command can be used for plotting the Laplacian kind of edge detected result of the filter. In this image, these two images, you can see that right side image have edges of the left side image. Now the next filter based on the second order derivative is Laplacian of Gaussian. Means we are applying Laplacian to Gaussian filter. This filter was introduced by Hildreth. This filter is really very well for the transition of the gray variable where there is abrupt changes. This filter is Gaussian based, which uses Laplacian to take second order derivative. Laplacian works on the zero crossing method. Therefore, when second order derivative crosses to 0, then the particular location corresponds to the maximum level. This you already know that if second order derivative is 0, then there is maxima and minima. Here the Gaussian operator reduces the noise and Laplacian operator detects the sharp edges. So both advantages there. You already know that Gaussian filter is used to reduce the noise and Laplacian is used to detect the edges. Therefore, by Laplacian of Gaussian we can do both in one end. So the equation for Gaussian is gxy upon sigma root over 2xy e to the power x square plus y square upon 2 sigma, and Laplacian of Gaussian, if you apply this second order derivative to this, that is del upon del x square gxy and del upon del x square for gxy and y, then it will result in x square plus y square minus 2 sigma square upon sigma to the power 4 e to the power minus x square plus y square upon 2 sigma. Now we have to implement this in Python. Applying the second order derivative, we have to take one integer first, integer size of sigma, and then I am creating one mass grid of the size, whatever size is of the coming from the image. Then I have written the equation in the Python. The equation that I have just shown, this equation is written in the Python, and then I have created the kernel using this equation, this defined definition of this defined function for log second order derivative. Once kernel coefficients of the filter is generated, then you can apply the Laplacian log operator, I am saying log operator of the image. So to apply this, you have to use the convolution. The convol 2D command is available, so you can apply this convol 2D command to the image and write this same so that the result remains the same. Now to see the original image and the resultant image after this Laplacian of Gaussian based edge detection, you have to use plot comparison command. The one algorithm based on this filter, that is called Canny algorithm. So Canny algorithm is very famous and very effective for edge detection. This is very nice method for edge detection, and this was introduced as an edge detection operator that uses a multi-stage algorithm to detect wide range of edges in images. And starting this algorithm was developed for the grayscale images, but now you can by using the RGB color system or RGB planes, you can apply to the color images also. It was introduced in the year 1986 when microprocessor was introduced and developed by John F. Canny, scientist. Canny also produced computational theory for edge detection, explaining why this technique works. Canny edge detection algorithm is composed of 5 distinguished steps, and every step is very nice. Let us see. The 5 stages of or 5 steps of Canny edge detection are: first one, noise reduction; second one, gradient calculation; third one is non-maximum value suppression, and fourth one is double threshold length; fifth one is hysteresis, means tracking the edges of image with the help of hysteresis. We will see every algorithm and we will implement in Python every steps in detail. The algorithm is based on grayscale images, but don't worry, this can be applied to color images, this can be applied to videos too. Therefore, image in starting, just we are converting the image to grayscale and we will follow the steps for the grayscale. First step is noise reduction. Noise reduction, you know that for reducing the noise we need some filter of noise reduction. Since the mathematics used here requires the derivatives like gradient calculation, therefore edge reduction results are highly sensitive to the noise, because if noise is there on the edge then result will be different. So noise reduction is very important before going to the edge reduction. So the Canny has given the model that you first go for the noise reduction, and the filter used by him for noise reduction was Gaussian. To do so, image convolution technique is applied with Gaussian kernel. So here you can use any size of the Gaussian kernel. You can take 3 by 3 size of Gaussian, or 5 by 5 size of Gaussian, or 7 by 7 size of Gaussian, etc. But the size should be taken appropriately. The filter kernel size depends on the expected blurring effect. If you want a small blurring effect, then smaller kernel, and if you want larger blurring, then larger kernel. But it should be compromised, or it should be decided properly. In this example, in my example, I am taking even 5 by 5 Gaussian kernel or Gaussian filter for this. Here you can see I have defined the Gaussian function. I could have used the standard function of the image library, OpenCV library, but I have written the function here so that you can understand it well. For your understanding purpose, I have written the detailed function here. The size of the image, and it takes sigma values. So size calculated and created one mass grid and applied the Gaussian function to the mass grid, and this will result the Gaussian values. And this Gaussian kernel of 5 by 5, or you can take for your purpose, or 5, and then you can apply this using the 2D convolution command. So command is convol 2D. This, and you can apply this. Do not forget to write same and symmetric, that we have to use the symmetric filter with the same size. So the result of the filtering will be same as the size of the image, because if you remember the convolution, in convolution process the size of the result is higher as compared to the input, L1 plus L2 minus 1. If you remember the 1D convolution method, in 1D convolution the size of the resultant is equal to the length of first signal, then length of second signal plus 1. But here there is the way that we can maintain the same size by using this same command. Then at last you can compare the original image and resultant image. Here you can see that after this first step, applying the Gaussian blur, the image in the right side is better as compared to the original image. Second step of Canny edge calculation is gradient calculation. The gradient is for the purpose of edge detection. This is the main step of edge detection. So this depends on this detects actually the edge intensity direction by calculating the derivative or gradient of the image with the help of edge detection operator. For edge detection there are many operators. I have already discussed Sobel operator, Prewitt operator. So here the operator that is used is Sobel operator. You can use other operator also, because I am going in detail. So you can change the operator and you can have your own way. But Canny used Sobel operator, therefore I have used Sobel operator. And when to detect the easiest way is to apply the operator that highlights the change in both direction, x and y direction, and then you can implement the combined or absolute value of these two, and then the overall operator can be applied to the image. But here we will take magnitude and phase, both can be calculated. Magnitude can be calculated by root over ix square plus iy square, and phase can be calculated by using tan inverse iy upon ix. And this Sobel operator can be applied to the image. The Sobel operator values, you already know that we have to have -1, 0, 1, -2, 0, 2, then -1, 0, 1 again for x direction. For y direction, a conjugate of this matrix, and then I am taking Ix and Iy, Ix for x direction, Iy for y direction, and taking the absolute values of these two to get the overall detection of edges. Absolute value will represent magnitude of the result, and also calculating the phase by in the terms of theta. Here you can see that edges are properly detected. You can stop here if you want. Canny could have stopped here, but here the problem is that all edges are not detected. Also in the edges, the pixel values, bright pixels, are not of same intensity. Therefore, further 2 steps has been devised by the Canny, and those 2 are also important. Let us discuss about them. So the third step is non-maximum suppression. The result was almost expected one, but the edges are somewhere thick and somewhere those are thin. So the non-max suppression step will mitigate this problem. Moreover, the gradient intensity level is between 0 to 255, which is not uniform. The edges that are the final result should have the same intensity. That means all the pixels should be 255. Therefore, ideally the final image should have thin edges. Thus, we must perform a non-maximum suppression to thin out the edges. The principle is simple. The algorithm goes through all points of the gradient intensity matrix and finds the pixels with the maximum value in the edges direction. Each pixel has 2 main criteria: edge direction in radian and pixel intensity between 0 to 255. Based on these inputs, non-maximum values are suppressed. Steps are as follows. Number 1, create a matrix, initialize with the 0 value, same size as the original image. Identify the edge direction based on the angle and the value of the angle, then check the pixel in the same direction that have the higher intensity than the pixel values currently processed. Return the image processed with the non-max suppression algorithm. You can see the result that in the left side there is maximum, is somewhere there is brighter, somewhere there is lighter, but in the right side everywhere there is same. That is the result of non-maximum suppression. In this result, the same image with the thinner edges somewhere, and however there is some variation regarding the edges intensity. Some pixels seem to be more brighter than the other, and other way to recover the shortcoming will do the final step. The double thresholding aims at identifying 3 kinds of pixel: strong pixel, weak pixel and non-relevant pixel. Strong pixels are the pixels that have intensity so high that we are sure that they contribute to the final edge. Weak pixels are the pixels that have an intensity value that is not enough to be considered as strong ones, but not small enough to consider as non-relevant. Other pixels are considered non-relevant for the edge. Now you can see what the double thresholding holds for. High threshold is used to identify the strong pixel intensity higher than the high threshold. Low threshold is used for the identification of the non-relevant pixels. All pixels having intensity between these 2 thresholds are considered as weak pixels. By doing this step, you can see the result. In this result, many of the pixels are highlighted. The last step is the hysteresis step. Hysteresis mechanism is the next step that helps us to identify the ones that could be considered as strong and the ones that could be considered as non-relevant. Based on the threshold result, the hysteresis consists of transforming weak pixels into strong pixels if and only if at least one of the pixel around the one being processed is a strong one. So after this hysteresis, you can see the result that it is detecting most of the edges inside the image. We can see that there is there are the edges. Now we have done edge detection with the help of 3 operators, and the operators works well for the edge detection as edges are coming out after the operation at the end of the session, and we have understood the images, edge detection, gradient based techniques, Sobel operator for edge detection, Canny operator for the edge detection, and advanced method of edge detection such as second order filters, Laplacian operator, Gaussian of Laplacian operator, etc. And as I always say that the codes will be given to you in the publicly available repository of me, that is on github.com Dr.Atul/image filters. You can download the codes from there and you can practice them. I hope you all will explore new techniques for edge detection based on the foundation that has been made in this session. Thank you all. Happy coding. Meet you again in the next tutorial.